Hello everyone, I am Nipuna Veerasekharan. I am a researcher at Scholar and I will be presenting a demonstration titled Large-Scale Analysis on Vulnerability Remediation in Open Source JavaScript Projects. Vulnerability introduction in a project is inevitable, and from our experience, we know that vulnerability remediation is a phase that every software project has to go through. We observe the security of a software project relies mainly on vulnerability discovery and remediation. Our motivation for the study comes from the lack of studies understanding the effectiveness of the vulnerability remediation phase. To that end, we utilize the source code analysis using static code analyzers. We selected a set of widely used JavaScript repositories hosted on GitHub platform with the selection criteria where repositories with at least 500 commits and at least 2 commit authors. Then, for each repository, we analyze the source code from the first commit to the latest commit using CodeQL static analyzer. We created a timeline of vulnerabilities introduced and fixed throughout the history of the repository using the static code analysis results, and we defined commits as follows. We define intercommit as the commit CodeQL identifies a vulnerability for the first time in the code. We define fix commit as the commit responsible for fixing a given vulnerability. And we define intro plus fix commits where a commit that introduces a vulnerability while fixing one. Our analysis pipeline has analyzed 130 open source repositories comprising around 501,000 commits, and our pipeline has discovered 80 unique security vulnerability types where on average 170 instances of security vulnerabilities are found in repositories. We observe intro plus fix commits in 117 out of 130 repositories where it accounts for 90% of total repositories. We identified that in certain repositories, as much as 7.15% of developers are responsible for intro plus fix commits, and 54% of the time, the intro commit and the intro plus fix commit were committed to the repository by the same developer. Another interesting finding is that 7% of the developers who committed intro plus fix commits have contributed to multiple repositories, which shows that they are active open source contributors. We compare the published date of common weakness enumeration numbers associated with the discovered vulnerabilities and the vulnerability introduction date, and we observe that 78% of the time, developers have committed a publicly known vulnerability. Also, we observe that on average, projects have repeated 75% of vulnerabilities. When considering the vulnerabilities, which are categorized under OS top 10 vulnerabilities, we observe 2% of all intro plus fix commits have introduced at least one OS top 10 vulnerability. Interestingly, 37% of the time, developers have fixed a less severe vulnerability, while there are high severity vulnerabilities that exist in the source code. With the earlier mentioned findings, we observe that successful vulnerability remediation is critical to software security. However, in reality, due to the finite resources, developers cannot fix all the vulnerabilities discovered in the source code. Therefore, they require a vulnerability prioritization scheme on a file level. We develop a prioritization scheme where it measures the severity of the vulnerability, the density of the vulnerability spread, age of the unfixed vulnerability, and the proneness of repeated vulnerabilities introduction. With our vulnerability distribution visualization, a developer can identify which file needs more priority for remediation. As shown in the graph, our vulnerability distribution visualization shows where the intensity of the red color of each file is dependent on the prioritization score. Each file in the source code has provided a vulnerability prioritization score where it is comprised of severity score, sibling score, intro plus fix score, and the lifetime score. With the research outcomes, we present Sequza, a web-based system to view the overall security posture of a repository, and it aids the developers in prioritizing vulnerability remediation. The key idea behind Sequza is where first identify vulnerabilities, prioritize the vulnerabilities according to the prioritization score, and remediate the identified vulnerabilities. As the overall architecture of Sequza, it is comprised of Sequza core, where it handles all the analysis tasks and stores the results. Sequza API provides access to the analysis results. Sequza RQD provides central maintenance, while Sequza Dashboard is the user interface where users can interact with Sequza system. Now let's move on to the demonstration of Sequza. As you can see, logged in users can use our system to queue repositories for analysis. Before that, the users need to authorize providers. Currently, Sequza supports GitHub and Bitbucket as providers. Now, the users can view all their repositories from the authorized providers. The users can select a repository and queue them for analysis. Currently, Sequza supports repositories written in JavaScript, Python, Java, and C++. Now, the users can view the currently analyzing repositories. In this dashboard, the users can view the analysis completed repositories and the currently analyzing repositories. Now, after a repository is completely analyzed, the users can view the analysis results. In the results head view, the users can view the overall security posture of the repository. It gives the overview of the number of intro commits, number of fixed commits, number of intro plus fixed commits, and the number of unfixed commits. And it shows the last analyzed commits as well. Now, the users can select a commit to view the fine-grained security posture of that commit. The users can view the basic commit metadata such as commit message, author, and date. Then, the users can view the vulnerability distribution of the selected commit. For each file, in the specific commit snapshot, the prioritization score is visualized. The intensity of the red color is proportional to the score. Now, the users can view the fine-grained score breakdown for each vulnerable file. The view shows the overall vulnerability score for the commit. The score breakdown table shows for each file the severity score, the sibling score, the intro plus fixed score, and the lifetime score. Then, the users can view the vulnerabilities detected in each file. In this view, it shows the detected vulnerabilities, the associated CWE numbers, and the detected line numbers. Additionally, the users can view the dependence of these vulnerable code lines. If the users want to compare two commits, they can select two commits from left and right drop-downs. The users can directly compare the overall score from the view. If a selected commit is identified as an intro plus fixed commit, it is immediately notified to the user. The user can view the vulnerability scores for the entire timeline of the repository using the results head view. The users can view the overall summary of their analyzed repositories from the statistics view. It shows the analysis results summary for each language and for each repository under the specific language. In our study, we present a novel automated analysis pipeline to quantify the vulnerability remediation phase using intro commits, fixed commits, and intro plus fixed commits. We demonstrate our tool Sequza to aid vulnerability remediation, which is the combined outcome of our study. With this, we conclude our demonstration. Thank you.